Okay, so in the very first model that I made a video of, we had a diffusion in a pipe. We had 10 milligrams per cubic meter at the left side, and we had 0 milligrams per cubic meter fixed on the right side. So this problem was a Dirichlet or a model problem where we had Dirichlet boundary conditions in both ends of the pipe and only diffusion to the right side of the domain. So I have loaded that model that you have already seen, and it looks like this. We could be a little explicit here by saying that dc/dt at position 0 is equal to 0, and dc/dt at the last position is also equal to 0. So this just means that we have a Dirichlet boundary condition at both ends, that the derivative does not change. It is equal to 0. All right. Then we made the initial condition array here, and we set the left side, the first index, to 0 as the initial condition. Let's try to run all this to start with. Good. And we can see C0 is now an array with zeros, except at the very left side where we have 10 milligrams per cubic meter. If we run this model for 1000 seconds and we solve it with solve-IVP and we then plot it, we get this figure. So of course we have 10 milligrams per cubic meter on the left side, that is 0 meters into the pipe, and on the right side almost well at 0.8 meters, which is close to the end, we have the concentration is not really increasing yet. Good. So I show you this because now we are going to verify that mass is conserved in this model. And how can we do this? Well, like from class, we had the curve here, which shows the oxygen concentration over the different positions in the pipe. This is just a snapshot of any time in the system. So this could be, for example, the concentration at the different positions at the last time point in the simulation. It doesn't really matter which time you use, as long as you are using it consistently when you do this mass conservation. So I just recommend that you use the last time point in your model output and get the O2 concentration at all your different positions. We want to confirm this, that the sum of all this oxygen in the model domain is actually equal to what we totally put into the model. And what we put into the model is the fluxes. So the flux, which is grams per square meter per second, that is going into the model domain on the left side. And then we have a flux that is going out of the model domain, which is on the right side. Remember that this is gram per square meter per second, but we want to cumulate the flux. So we want the flux over the complete time period that we simulate. Then we should get the cumulated flux that has gone into the model domain after the total simulation time, which is what we compare with in the NP traps for this one. Okay. So as you can see, the flux is defined like this. Jn is minus diffusivity times dc dx. And we need to calculate this now from the output. Okay, so we go into our model and then we look in our solution, which is up here. We go into Y and then we have a look. So the different rows here represent the different positions in the in your model domain. So this is at the boundary and this is at position 1. And so the difference between the left boundary and position 1 will give us DC. Okay, so we write this down here. Let's close this. So flux, we call it J, which is equals to minus D times dc dx. And if we discretize dc dx, we get this. J is equal to minus D times C1 minus C0. And let me put the right parentheses. Divided by dx. Okay. We have to use this one-sided difference because we don't have the position. We cannot do central difference because we don't know anything about what is on the left side of the domain in this situation. So let's calculate the flux. First, we extract the values at position 0. So we go into the solution. So that would be the first row and all columns. So the different columns in the solution will be the different time points. So this will give us the concentrations at the surface or at the left side for all times. We can do the same for position 1, that is row 1 and all times. Now we can calculate the flux, which is equal to, and sorry, let's just change this to C so we don't overrule the initial condition vector. 0, whoops. Okay, so this should give us the flux in at all times. Let's try to run that. And let's see how it looks. Good. So this is the fluxes at time 0, at time 1, 2, 3, 4, and so on. Of course, the real times they correspond to is given by sol t. So actually these are the times that correspond to the values here. So that's the flux in. Good. The flux out, what would that then be? Well, here we have to get the last point. We call it Cn. That is equal to sol y. Last point and all times. And then we can get the second last point. Again, we have to do a one-sided difference instead of the central difference because we don't know what the ghost point is equal to. Good. So we calculate the flux out Cn minus Cn2 divided by dx. Good. So the flux out here. So we get some very small numbers. Almost nothing is going out on the right side, it seems. Okay, so this is the fluxes at all the different time points, but we want to know what is the cumulated flux. What has, if you sum it up over all the time, how much has totally gone into the model domain. So we can use the traps, np traps function for this. We just pass in flux in, and we want to kind of integrate it over the time, and the time is in sol t. We can call this flux in cum. We can then do the same for the flux, the cumulated flux out. Here. So now we can say what has gone in minus what has gone out must be what has accumulated in the system. So this will be flux in cumulated minus flux out cumulated. We can call this net flux in. And we can print what the value is. Okay, 1.63 milligrams it must be. Okay. Now we want to compare this number with what is in the model domain at the last time point. So to get the concentrations at all the different positions at the last time point, we type this. Last O2, we can call it, is NP traps sol y. So here we want all the positions, but only the last time point. And we want to integrate over space instead. So that would be the x positions here instead of the time. And then we can print last O2. Okay. So we see that the last O2 here is a bit smaller than the flux going into the model. So obviously something is a little off, and the reason for this is that we only have an output of 50 time points. So let's increase this a bit so the solution gives us a lot more time points. This increases the accuracy of this flux calculation. So we solve it again with 1000 time points. Calculate all these fluxes again. And now we get the net flux of 1.546 and 1.59. So there's still a problem here. So what could this be due to? Well, the NP trap method here for the total O2 in the system at the last time point, that just calculates the sum of everything that's in the model. But the flux is just what is going in minus what is going out. So what if there was something inside the model domain to start with? Then that would increase this calculation over the flux. So we can just see C0, which was what it started at. And we see there was actually 10 milligrams per cubic meter at the left boundary to start with. So we have to subtract this from the last O2. So what is, this is just the concentration, but what is the mass? Well, we can multiply this by dx divided by 2. And only the first point here, which is where we have the 10, and see what that gives. 0.05. So let's take last O2 minus this. Then we get 1.5462. Okay, let's compare that to the net flux in again. And that also gives 1.5465. So there's a very small difference here, but they are almost identical. And I would say this is good enough that you can say that that you have verified that the mass balance or the mass is conserved. What about the case where we have the Dirichlet boundary conditions defined in with the other method? I will just copy over how that would look, because you have to do it a little differently in that case. So this is basically the same model, but instead of using the Dirichlet where we have it at the boundary, we have the boundary conditions one position to the left and one position to the right of the model domain in this one. Otherwise it's the same. So here we have to give the concentration to the left of the domain and to the right of the domain as extra arguments to make it work. Let's run that. and we run the solution. Okay, and now we have to do almost the same exercise as before. But now we can actually do, for the flux, we can do it with a central difference, which is a little more accurate than the one-sided difference we used before. So flux, we can now calculate like this, is equal to J equal to minus D times dc dx. And we can discretize it, then it gives J equal to C C1. Well, let's just do it with I first. Minus C I minus 1 divided by 2 times dx. And why can we use the central difference method here? That's because we want to calculate the flux at the position 0 and the last position. And here we actually have the ghost points. We have C left and we have C right. So this would actually be C left, and this would be C1 for the 0th position. So it would be like this. Flux on the right side, or on the left side, sorry, would be like this, minus D times C1 minus C left divided by 2 times dx. So that is the central difference formula for the first derivative. Okay, let's yeah, so of course we have to just extract the concentrations first. It doesn't know what C is here, so C1 we will make here. Sol Y, that is rho 1 and all times, then we just put C1 here. Now it should work. Good, and for the flux out we have to calculate the second last point. If we want to make the central difference, we call it Cn2. So Y minus 2 and all time points, flux out equal to C right minus Cn 2 times dx. So here we have written the, again with central difference of the first derivative, like this. Let's run that. And now we again calculate the cumulative fluxes in and out. And we say flux in. And then it would be with respect to time. And flux out cumulated is equal to flux out sol 2. And we subtract them from each other. Call it net flux in. Let's print it. Okay. I think we forgot something up here, because when we use this other method here, where we have the boundary conditions to the left of the model and right of the model, Then we also have to change the initial condition. No, we already did that here. Okay. Let's just run it again here. Oh, this is the reason. We forgot a sol2 here and here. Looks right. Okay, that looks better. 1.498. And now we compare it to the the integrated concentration over the whole model domain. And here we use the sol y, and we need the last all positions and the last time point. And we integrate it with respect to space now again. And what does that give? So here we see it gives almost the same as the net flux in. I can print it here. So there's a difference on the fifth decimal here. And here we don't have to subtract the initial condition because there was nothing to start with here. It was 0 up here. So that's okay. So this is how you verify that mass is conserved in your model.